Hello everyone, and welcome to the first session of this lecture series entitled Excel in Structural Engineering, where I will be trying to help you understand how to incorporate Microsoft Excel into your civil engineering applications in general and structural engineering applications in particular. The Excel applications that I will attempt to help you develop require prior knowledge of structural engineering fundamentals. I will start from scratch in terms of Microsoft Excel, but you will have to revise your structural engineering concepts and do a lot of practice and self-experiments on your own in order to be able to keep up. I will be using the American Concrete Institute Committee 318 Code of 2019, which was reapproved in 2022. In short, it can be abbreviated as the ACI 318-1922 code. I will also be using the Standard International System of Units. Nevertheless, the principles shown in this lecture series can be applied to any other code and system of units. Let's say that you are a structural engineer working in an engineering firm, where you are responsible for analyzing and designing reinforced concrete beam cross-sections, for example. Let's keep things simple at first. One way of doing it is to manually analyze or design each cross-section, which is time-consuming and cumbersome. Another way of doing it is to automate the process, commanding your computer to do the bulk of work, which gives you the time to work on improving your engineering judgment and optimization. Let's say we are interested in calculating the design strength, which is phi times Mn, for the singly reinforced rectangular beam shown in the figure. Given to us are the dimensions of the beam and steel reinforcement, as well as their material properties. Again, one way of analyzing the beam can be carried out through manual calculations, where the engineer will have to perform the required calculations by hand over and over and over again during his or her working hours, which isn't very efficient or fun. Another way is to ask the computer to do the bulk of work in a second and better utilize the time on enhancing our engineering experience. Note that the two longitudinal bars located in the compression zone are hangers used in order to hold the stirrups in place. If these two bars are totally ignored, as is the case in this example, then the beam can be treated as singly reinforced. If the bars placed in the compression zone are used to increase the ductility of the beam or reduce the midspan deflection, for example, then these bars are called compression steel, and their contribution to the flexural capacity renders the beam as doubly reinforced, which is a topic that we will deal with later on. Manual calculation of the design strength requires calculating the centroid to each steel reinforcement layer. Then the centroid of the total area of steel is calculated. These centroids are shown here. And they are required to calculate the effective depths from the total depth of the cross-section, denoted by small letter h. These calculations are shown here. For YB, which is the centroid of the layer farthest from the neutral axis, YT is for the layer of steel on top of it, and Y bar is the centroid of the entire area of steel. The reinforcement area and reinforcement ratio are calculated and compared to the minimum allowed by the ACI code. Then we will have to calculate the depth of the Whitney rectangular stress distribution, denoted by the small letter A, from which we can obtain the depth to the neutral axis, denoted by the small letter C, using the correlation coefficient beta 1. Section ductility can be checked by either comparing the C over dt value of the cross-section at hand with the C over dt limits specified by the ACI code, or by comparing the strain at the layer farthest in tension, denoted by epsilon t, in our cross-section to the strain limits specified by the ACI code. Once the section is determined to be tension controlled, where the strength reduction factor phi is equal to 0.9, we can then calculate the nominal strength Mn and multiply it by the strength reduction factor phi to obtain the design strength of the cross-section. Instead of all that, and remember, here you are performing the calculations for one beam only, we can create a template in Microsoft Excel to perform all the required calculations in a blink. Not just that, but the template can also perform all the checks required by the ACI code to determine whether the section satisfies the ACI code requirements or not before calculating the design strength. First of all, by looking at this template here, you can see that the template is locked and protected against unwanted changes made by the user. The output cells display the results while their formulas and equations are hidden, all of which are concepts that we will learn here. The user can only enter the input parameters, and the template will perform all the checks, and if the beam is adequate, the template will provide the design strength value. If the section is not adequate, as is the case shown on screen, where the width of the beam, denoted by the small letter B, 300 millimeters, is insufficient to encompass 6 bars in the bottom layer of steel, the template will indicate that the section does not satisfy the ACI code requirements by displaying red colors and will not calculate the design strength of an inadequate section. If the input parameters are changed to define an adequate section, for example, the design strength will be provided and the conditional formatting settings will change the color to green, indicating that the section has passed. The results obtained from the Excel sheet shown on screen can be dynamically linked with a graph that shows the status of the beam cross-section. The section can be in the tension-controlled zone and therefore accepted by the ACI code 2019 or 2022, changing the input parameters, for example, by increasing the amount of steel reinforcement here to 22 millimeters and 22 millimeters. This will render the section as inadequate as it travels from the tension control zone to the transition zone. Further increasing the amount of steel will shift the section into the compression control zone. For example, if we have here 28 and 28 millimeters, then the section transfers to the compression controlled zone. Only tension controlled sections are accepted by the ACI code 2019 and 2022. Remember when I told you that you have to revise your structural engineering and reinforced concrete fundamentals in order to be able to keep up and to understand what we are talking about. Note that if you try to place a bar diameter in the second layer that is larger than the bar diameter in the layer farthest from the neutral axis, the template will show a red color indicating that the larger bar diameter should be placed farthest from the neutral axis in order to have a more efficient layout of steel. For example, if we have the bottom steel 16 millimeter bars while the top steel is 28 millimeter bars, then the template will show red color indicating that this is not an efficient layout of steel in the different layers. Furthermore, if you try to place more bars in the second layer than in the first layer, for example 2 in the layer farthest from the neutral axis and 4 in the layer on top of it, then the template will show a red color again, indicating an inefficient use of the material in the cross-section. And the layer farthest from the neutral axis should have the larger number of bars when compared to the layer on top of it. And the layer farthest from the neutral axis should have the diameter of bar that is largest for more efficient use of steel in the cross-section. The Excel template presented so far in this session required no programming, while other Excel templates, such as the one shown on the screen now, which is used to analyze doubly reinforced concrete cross-sections, and we will be learning all about it in this lecture series. This template will require extensive programming, where the Visual Basic Application Portal, or VBA in short, will be used to control whatever is happening inside the Excel template. In this template, iterative numerical analysis is used to calculate the compression steel stress level, where the user controls the number of cycles to be performed. We can change the number of cycles here to 10 or to 3, which is what you actually need in most problems, or we can even have it to 25. The Excel command button is used to order the template to print the results of each cycle in a new formatted table. The results of the Excel template are linked to a graph that shows the status of the beam in terms of the ACI code, where the cross-section can be in the tension, transition, or compression controlled zones. And there is another figure as well that shows the convergence of the iterative numerical procedure. There are other methods to calculate the compression steel stress level, but I like to link engineering with applied mathematics whenever I can. If you are interested in learning how to develop these Excel templates and much more, then this is the right place for you, and I will be talking to you again in subsequent sessions. Best wishes.